Hello everyone. Namaste. Good morning, good afternoon, and good evening. Well, it's late evening here in Nepal, and we are here back again with brand new episode of webinar on geoscience for sustainable development. This is Suraj Gautam, a civil engineer and disaster risk reduction professional from Institute of Himalayan Risk Reduction. First of all, I would like to welcome you all in our Himalayan webinar series. Institute of Himalayan Risk Reduction is an organization established with a vision to prepare risk-informed societies for disaster resilience and sustainable development. So, to contribute onto this, IHRR has been regularly organizing Himalayan webinar series on geoscience for sustainable development and disaster risk reduction and management. So far, we have successfully organized 8 episodes of webinar on geoscience for sustainable development. And yes, today it's the turn for the ninth one. And today we'll be having an interesting topic on hydropower in the Himalayas, a risky endeavor, which will be presented by Dr. Wolfgang Schwanghart. On behalf of the organizing team, we are really grateful to our presenter who will be sharing us with his insights and healthy experiences. So it is indeed an honor to welcome our presenter, Dr. Wolfgang Schwanghart, who is research associate at University of Potsdam, Institute of Earth and Environmental Science, Germany. To make this session more interactive and lively, we have Assistant Professor Dr. Basantaraj Adhikari from Institute of Engineering, Tribhuvan University as our session moderator. Dr. Adhikari is also the visiting scientist at Institute of Himalayan Risk Reduction. We'd also like to welcome all of our participants and regular attendees who are joining us through our social media live streaming and also through this Zoom platform. This webinar has also been featured in the website of Relief Wave and Prevention Wave. And talking about the webinar registrations, till date, we have more than 239 registrations from different parts of the globe. So to address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction, and we'll be receiving the queries and feedback from our social media live streaming as well as from our Zoom chat box. And we have been organizing this webinar series on geoscience for sustainable development on a regular basis. We believe this webinar series has been supporting our early career scientists, DRR professionals, academicians, and all the participants. And yes, it's a beginning and we'll have a long way ahead. So before starting our session for today, I would like to share some brief introduction about the Institute of Himalayan Risk Reduction. IHRR is a research institute established with an objective to assess and understand the risks to contribute for the sustainability. Our team constitutes of professionals with expertise and experiences in the field of disaster risk reduction, in understanding the risks, conducting academic research, and field level implementations in Nepal and across the globe. So IHRR has a vision of preparing risk-informed societies for disaster resilience and sustainable development. And we have a mission to prioritize, train, and mobilize DRR professionals and promote promote the solutions through science, engineering, technology, and innovations. And we have 4 thematic areas, which includes the DRRM consulting, research and development, disaster academy, and youth in disaster risk reduction and management. So far, we have successfully accomplished a number of projects that includes the transboundary project, hazard project, risk assessment project, where we conducted a landslide risk assessment on Sino-Nepal Sino-Nepal road corridors. We have also collaborated with the local government, and also during this COVID-19 response, we collaborated with a number of organizations to contribute for the development of national platform for the COVID-19 response, and which was endorsed by the Ministry of Health and Population. So this portal is capable of disseminating the information regarding the COVID-19 dedicated medical facilities and so on. Besides, we have also been working with the local government to bring out some innovative practices that includes the UAV surveying of Hetauda sub-metropolitan city. So we have had quite a number of engagements, and it was also carried through the participatory approach. And besides, we have also enlisted our commitment in the Sendai voluntary commitment, which can be accessed in the website of UNDRR. So in this way, we have been working during this pandemic period as well. And besides, we have been regularly organizing the webinar series on geoscience for sustainable development and disaster risk reduction. And today, here we are for the yet another interesting webinar on the hydropower in the Himalayas, a risky endeavor. So without any further delays, now I would like to move on, and I would like to share some house rules for this webinar. The audio and video of the participants will be switched off. The overall session of the webinar will be recorded. For any queries, the participants can write up in the chat box or in the comment section of the Facebook streaming live. Waiting room has been enabled, and only registered users with their original identity are allowed in the webinar room. So we'd also like to request our participants to please rename and keep their name as mentioned in the registered link. Also, we would like to request our participants to strictly avoid using the annotations, and the feedback links will be provided during the session, and we'll be providing the participation certificates after the webinar. So without any delay, now I would like to move on, and may I request Dr. Basanta Raj Adhikari to please proceed further with his moderation. Thank you for now.
Thank you, Suraj. Do you hear me?
Yes, you are audible.
Wonderfully start, Suraj, about the introduction of Institute of Himalayan Risk Reduction. And today we are going to talk about the different aspects of hydropowers, how was the condition over there. And this topic is really important because lots of people are investing money to construct the hydropowers around this whole Himalayan mountain chain, starting from Pakistan to Bhutan. So, but there are lots of risks or hazards which are associated with this hydropower, which are already, some of them are already constructed, some are already financed, and some are already planned. But to understand this whole dynamics, how these Himalayan tectonics and Himalayan geomorphological or the glacial lake outburst plot or climatic associations are really important, not only for the power generation, but also to understand the larger scale dam construction for this storage project for hydropower, and what would be the effect if this hydropower fail in case in near future. So there are lots of aspects going on, and today in this scenario we have invited Dr. Wolfgang Schwanghart. He's my good colleague. We are working together for more than 10 years in Nepal, Himalaya, not only in Nepal, but also in Germany. So we have been working in this sector for a long time. Dr. Wolfgang Schwanghart, he's a research associate at the University of Potsdam, Institutes of Earth and Environmental Science, mostly working group in soil science and geomorphology. He completed his postdoc at the University of Potsdam, in the Institute of Earth and Environmental Science, working group on geohazard funded by Progress, which is called Potsdam Research Cluster for Georisk Analysis, Environmental Change and Sustainability in 2014. So he has more than 10 years of experience in working with and teaching in geographic information system, geographic database system, and statistics. He knows most of the programming language, including MATLAB, R, SQLs, and others. And he's involved in co-prepare, collaborating Indo-German project on estimating and predicting natural hazards in the Himalayan region. A DAAD collaborative project with the Indian Institute of Technology, IIT Roorkee. And he's also associate editor of the Journal of Earth Science Dynamics and Scientific Advisory Board of the German Working Group on Geomorphology. And we have, analyzed and this sedimentary signature in the Himalayas to develop the large scale valleys in Nepal, in Pokhara Valley, which was published in Science 2016. So Wolfgang was the team leader, and I was also the team member of that group. So I'm always enjoy working with him and talking with him. And so today also we'll enjoy his talk, and he's going to present hydropower in the Himalayas or risky endeavors. So Dr. Schwanghart, the floor is yours. Please proceed. Please unmute yourself.
So I guess you can hear me, and I hope you can see the slides. Hello, everybody. I'd like to thank very much Basanta Raj Adhikari and Suraj Gautam from the Institute for Risk Reduction for inviting me to give this talk today. It's really a pleasure to talk about hydropower in the Himalayas to you. And of course, I regret that I can't be there in person, but I think that on the other hand, giving this talk here online today is also a really great opportunity that we can exchange, you know, regardless of any borders, distances, and whatsoever we have in between us. So let me just start with my talk right away. I would like just to make a few key points before I start. And that basically also gives the structure of this talk. So what I want to show is that, well, Himalayan hydropower is on a steep rise with severe impacts on the environment. Second, that recent hydropower damages highlight the vulnerability of Himalayan hydropower to geomorphological extreme events. I will show a study that shows that, well, terrain analysis, so the analysis of digital elevation models, that this provides the tools and measures to characterize sensitive landscapes and to predict damages. So something that might be valuable for planning hydropower projects in the Himalayas in general. So what I will show is that accounting for geomorphological extreme events in the end reveals limits to hydropower expansion. Okay, so let me just get started. And well, with the first thing. So Himalayan hydropower is on a steep rise with severe impacts on the environment. So hydropower supplies a major share, about 16% of the world's total electricity. And that's about 72% of all the renewable electricity. So hydropower has an important share in the world's energy production. Now, the energy consumption, on the other hand, in emerging nations has recently been soaring, so skyrocketing and partly covered by hydropower expansion. That is particularly true for some of the Himalayan countries like India and China that have experienced a steep rise, as you can see here on that right-hand side curve, in energy consumption. And with that, it has also increased the share of hydropower. Now, this has led, in the end, to what is called a renaissance. So, a rebirth of large hydropower projects, which has been initially fueled by some international political decisions like the Kyoto Protocol's mechanism, the so-called clean development mechanisms, and the World Bank's development agenda. Nowadays, we still have that growth in hydropower with 450 large and 600 small hydropower projects applying for these clean development mechanisms. The Hindu Kush Himalayan region is expected to have by far the largest hydropower growth rates in coming years. What about in Nepal? Well, Nepal has a strong dependence on hydropower. Nearly 100% of domestic energy generation is done with hydropower. And well, what we expect is that there is a doubling of the energy demand until 2025, so compared to 2018. Which highlights that there is an extreme need for new hydropower capacity. So in general, that is very good development, actually. I mean, hydropower is a renewable energy, and there are a lot of other advantages. So, as I said, it's a clean, renewable energy. It's rather flexible, decentralized, and domestic. It provides, or it has the advantage that it could provide new sources of income in rural areas. If we generate or if we create reservoirs, these can offer a variety of uses, such as fishing, irrigation, or flood control. To this end, I mean, Nepal and Bhutan, for example, are endowed with high gradients, high topographic gradients, and a lot of water. So this would also offer revenue for Nepal and Bhutan in the long run. In particular, since these power plants usually have long lifetimes, especially the big ones. And well, there's also a very large untapped potential. So this is shown on the right-hand side here in this map from Gernat et al., which was published in Nature Energy. And well, you can see that there is a lot of remaining potential in the Ganges basin, which is shown here. So the largest untapped potential, well, which shows that, well, hydropower probably has a good future in this area, at least economically wise. However, besides these advantages, there are of course also some drawbacks, and these drawbacks are manifold. So, for example, there are profound ecological risks which are associated with hydropower. Habitat fragmentation can hinder the migration of aquatic species and potentially endanger fish diversity. It can lead to this destruction of wetlands, alterations of flow conditions, and well, reservoirs in the tropics are known to emit methane. So this will probably offset some of the offsets or of the benefits for being a carbon-free, or more or less carbon-free technology. So the other risks that are associated with hydropower are that, well, climate change will have some influence on the Himalayan water cycle, in particular on Himalayan glaciers, and it's not completely sorted out how that will evolve in the future. To this end, there's also a lot of, let's say, problems arising. Hydropower often encroaches into areas used by indigenous people. Often these projects may lead to mass resettlements. And well, in the big picture, hydropower use increasingly appears as an issue in South Asian geopolitics. Okay, so there are pros and cons of hydropower development, and I hope I have listed some of these. What I have done, or what I haven't done so far, and what I'm going to talk about is about the problems that we might face in terms of natural hazards. And that's also, I mean, the main subject of why we actually meet here as part of this web seminar series, okay? So what I'm going to claim is that Himalayan hydropower has experienced quite a lot of damages in the past. And these damages highlight the vulnerability of Himalayan hydropower to, in particular, geomorphological extreme events. Okay, so what kind of risks or let's say processes, natural processes am I talking about? Well, hydropower is exposed to several processes, and these include landslides. The map on the left top basically shows the distribution of landslides that were associated with dams and reservoirs. So due to different reasons, but often these ones have been fatal. There are earthquakes that directly impact on infrastructure. So what is shown here are cracks on a dam, which have been then closed again. But there are some direct impacts. of earthquakes on hydropower projects. There are glacial lake outburst floods. There's a huge body of literature that deals with the causes and effects of glacial lake outburst floods. One of the most important, one of the first ones that highlighted the influence of on hydropower is the one by Wishart and Zimmerman, who showed, and this image shows here actually, well, you can't see it probably that well, but that a Gloff destructed in 1985 along the Botikoshi hydropower station completely. So, and down here, well, the last problem are probably floods. This is just a hydropower project that was hit during construction during the 2013 floods. Okay. Now, what I want to focus on today are, first of all, two different events that had a strong impact on hydropower development in the Himalayas. So, first of all, now what you can see here on the bottom is a timeline of the counts of damaged HPPs, which we compiled in a literature study. And so you can, for example, see the Gloff that destroyed here, Botikoshi hydropower projects, and then several other ones. And then we see that steep increase in the last years. It's probably not exhaustive, our database, but what it basically shows is that there are two major events that had a large impact on Himalayan hydropower. First one is the so-called Indian floods in 2013, which damaged more than 25 hydropower projects severely. And the second one is the Gorkha earthquake in 2015, which led to a temporary loss of more than 30% of Nepal's hydropower capacity. So I think that these events highlight the vulnerability of hydropower infrastructure to natural extreme events. And that these losses undermine actually strategies that are there towards a sustainable development and use of hydropower. Well, let me show you a few pictures. This is some of the remnants of the 2013 Indian floods, and it shows 3 pictures of the hydropower project Vishnu Prayag. Well, on the left, there's Vishnu Prayag before the floods, and for scale, and for orientation, you can see that building here. That building is not shown here during the floods. You can see the roaring waters that pour down that river. So that house should be somewhere here. And then after the floods, it's here. So you see the massive scale of aggradation that this hydropower project experienced, and that also led to the destruction of Vishnu Prayag. This is an example of the Gorkha earthquake. What you see here is Google Earth imagery of Upper Trishuli. And well, on the left-hand side, you can see the, before it was actually constructed, an image of 2009. Then in 2014, it was constructed. I hope you can see it. And then in 2015, shortly after the earthquake on 25th April, you see the massive amount of landsliding that's just happened next to the hydropower project, and which then ultimately led to a massive aggradation also here in that area that more or less buried the hydropower project beneath gravels and debris. So the question that follows is, why were the damages to hydropower actually so high? I mean, hydropower projects are actually designed for floods and earthquakes with return periods exceeding 1,000 years or more than 1,000 years. So the question that we need to ask is, did these events actually have magnitudes that exceeded, I mean, statistically, a 1 in 1,000 year event? Well, Uttarakhand is the state that suffered most during the Indian floods. However, comparison of 3D rainfalls during the event with historical data, however, indicate that rainfall magnitudes were mostly below observed and estimated records. So here, for different climate stations, this is the Indian floods, and that was historical, so much larger. So everything that you find in that upper triangle, well, actually is our records that basically have experienced these kinds of floods, or where actually we have estimated 100-year return periods for such events. Clearly, this analysis neglects that there are potential accumulated effects like snowmelt and so forth, and these have also contributed to the severity of that event. But nevertheless, the major large-scale synoptic weather patterns that actually led to this catastrophe were actually quite well known to have happened and could also likely been predicted. What about the Gorkha earthquake? Well, of course, the Gorkha earthquake was one of the severest earthquakes that happened in Nepal in the century. However, based on instrumental and paleo-earthquake records, the estimated return periods are 80 to 90 years for the Himalayan range, so not 1,000 years, okay? So even when accounting for the lower regional probability, return times would be lower than 1,000 years. And even if it was, then this earthquake magnitude is not particularly high in the Himalayan context. So, for example, a study by Stevens and our work showed that, well, we could, or that actually earthquakes of magnitude 9 would be required to balance the slip rate deficit. So even these would be possible. Okay, so in the end, why do we have these losses? I mean, these were no 1,000-year events against which hydropower projects should be prepared. Well, of course, it's the economy, we could easily say, because values are connected to losses, of course. But, well, that's a bit too easy. I would say it's the geomorphology, stupid, okay? It's Earth surface processes that have been neglected in the design and assessment of the resilience of these hydropower projects. Okay, so what I want to show next is that terrain analysis actually provides the tools and measures to characterize sensitive landscapes, what this is I'll explain shortly, and to predict damages. So what is landscape sensitivity? Well, it's a concept that relates to the resistance and response to perturbations. Perturbations could be extreme events, they could be earthquakes or heavy rainfall events. And sensitive landscapes may respond to these perturbations with mass wasting processes. That's a quickly reaction to external shocks. So often landscape sensitivity may also reflect inheritance from past environments. They might also be associated with weak bedrocks. But however, I think that they usually are associated with what is called transient landscapes. So landscapes that are far from an equilibrium, a dynamic equilibrium in Heck's sense, and which is often the case in those areas that experience rapid uplift rates. Now, this is an example of a transient landscape. It's not in the Himalayas. It's the lower Yellowstone waterfalls, Yellowstone Canyon. So what's special about here? Well, what you see is that this landscape is responding to an upstream migrating nick point, that waterfall, which incises into some basalt layers. Now, what's so special about it? Well, what captured well, my attention is those hill slopes that are just downstream of the waterfall and that seem to be highly active. I mean, if we think that vegetation cover is a good proxy for the activity, for the geomorphic activity, then these slopes look highly active, okay? And now, okay. Do you still hear me? Okay, now you should hear me again. So up here is, again, this Yellowstone lower waterfall, and you can see that canyon and the water flow is in this direction here. And that nick point was migrating upstream, and what you can see is basically that it takes a while until the slopes basically recover or the vegetation recovers the slopes, which suggests that there's, that hill slope processes come to, again, to a dynamic equilibrium with the surrounding, or get more and more stabilized at least. So what we have is actually that there's an interaction between rivers that insize into a mountain chain or into a landscape, that this has an effect on the adjacent slopes. And that effect might be a bit delayed, might take some time until hill slope reaction or hill slopes have adjusted to a new equilibrium set by the base level of the river. Okay. Now, rivers obviously affect hill slopes. On the other hand, there is the other way around. And often this interaction, or often we can observe rather that interaction between incising rivers and hill slope response. Now that's a nice study by Antonio Scolli and his colleagues, which basically shows a cycle that can undergo, or that hill slopes can undergo as a response to incision. Now here's the initial position, then the river incises. That will trigger a response, perhaps even a bit of a delayed response, causing landsliding. Landslide material will be delivered to the river again, which then will cause new nick points or new aggradation of the channel itself, and then a readjustment to the initial position. So we can actually have these kind of feedback cycles with significant delays in them between river incision and hill slope response. Okay, so hill slope then, or hill slope response then may actually lead to the transport and delivery of huge boulders and hill slope material to the rivers themselves. And these actually showed some nice pictures from Nepal. From the first one is from Georgie Bennett, which actually has a project here in Nepal on boulders. And the other one is from the science paper of Kristen Cook, which showed that this material that is delivered to the streams can be actually quite dangerous for infrastructure that is located alongside the streams. Okay, so we see that terrain definitely has an influence on the geomorphological response of that happens along Himalayan mountain rivers. And so the next slide will show just the basis for the modeling work that I want to do. So, or what I did. So what you see here is basically a landscape evolution model. Okay, so we are jumping somewhere else now. Now this is just a hypothetical landscape that undergoes waves of incision. So it's basically a dome uplift, and then rivers incise into it, and what we change are uplift rates and bedrock erodibilities. And we see that this leads to waves of incision, and that nick points migrate upstream, and that hill slopes respond to that. Now the equations that are responsible for these patterns that we can observe here are actually quite simple. They rely on basically river profile analysis. So what you see here is a river profile, just of a hypothetical river, which is just perfectly in balance. It's a concave upward river. Now what happens if you have an external perturbation? Let's say a base level drop. So that means then if that base level drops, then you will have that migrating upstream nick point that leads to incision and, well, will travel through the river network. And while it is doing that, well, what it generates is a reach of oversteepened river. Now, in the next step, I want to quickly show how to characterize these oversteepened river sections. Don't worry, these are the only equations that I show in my talk. So the entire model that I showed in the simulations and animations are basically based on this common model, which is called the stream power model. It says, well, that the change in elevation at a certain point along the river is a function, well, of uplift rate and the velocity of incision. So, and the common way to interpret or to deal with this equation is that we assume, well, that we are in steady state. So that means that we equal any elevation change to 0. So everything is neither moving up nor down. And then we can solve that equation for S, so for slope, and express, when we solve that for S, we can basically calculate what is called the KSN. KSN is what is called the steepness index, and it refers, or it's a topographic metric that measures the steepness of a river. So, of course, rivers always increase their steepness the farther we go up, but KSN basically accounts for this increasing slope the farther we go up, and by normalizing over the catchment area. Now, there is another way to do that. I don't want to go too much into detail about that, but KSN can also be calculated using what is called chi. And chi is nowadays frequently used, or is a frequently used metric by people in tectonic geomorphology. What it actually does, the so-called chi transform, is that it normalizes, or that it transforms the horizontal distance so that river profiles become linear. Okay, so they are not anymore concave up, but linear. Now, again, we can actually do the same here by calculating the slope in chi space. And the slope will actually always be the same. So we call that, or I'm going to do that like Rahul Devrani, who did that in the GRL paper, that this is a constant slope in, well, when we have a steady state river profile. But if that profile experiences a base level drop, well, that will generate a section with high M chi values. So in the next few minutes, I'm going to, I said this, well, that M chi is what I'm using here as a way, as a means of characterizing oversteepened river sections. Okay, that's just one more animation that shows M chi or KSN. It's actually the same. That shows that this frontier that travels upstream is actually the part of the river network that shows these high KSN values, given everything equal, like same uplift rates everywhere and bedrock erodibility. Okay, now let's use this metric to model damage from the Gorkha earthquake. Now, the common way to do that is that there is ground shaking and that this will have hydropower project damage. So, like shown here, we have increasing ground shaking. We expect if there's a threshold exceeded, there is increasing damage. Okay, so I want to change that a little bit by including geomorphic activity And this geomorphic activity is, on one hand, of course, modulated by ground shaking itself, but on the other hand, by landscape sensitivity. So I'm using here landscape sensitivity on the y-axis and ground shaking on the x-axis. And I would say the further we go up here in that, to that right upper part here, the higher the damage will be. If we are in areas with a low landscape sensitivity and low ground shaking, well, that's okay. Okay, how can we test that model? Well, I'm doing that for the Gorkha earthquake in 2015. And what I'm taking is, well, for ground shaking, I'm using peak ground acceleration. So the amount of shaking that a landscape experiences. And I'm getting the data from ShakeMap. And well, it's damages to hydropower projects were both made by the main and the aftershock. So I'm combining those two maps into one map. So just the maximum of shaking that occurred during those two events. Then there is some data that we compiled on hydropower project damage. So in total, we have 41 hydropower project damage records. We retrieved those from gray literature, such as newspaper articles, websites, hydropower company websites, and so forth. And we classified the damages that hydropower projects had in an ordinal scale. So 0 was no damage at all, 1 is low damage, 2 moderate, so being out of operability for a few months, and then finally severe damage, which is either for many years out of operability or completely damaged. So we have these 41 records, and you see the map of these 41 records over there, and the distribution of the hydropower project. Well, then, geomorphic activity, well, we can rely on different data here. We used mapped landslides, which were shortly mapped after the earthquake occurred in response, or as an emergency response. So that one was published by Humdada, and I think it was done by the Durham University and colleagues. And then finally, well, landscape sensitivity. Well, here I'm just using that MCHI metric that I introduced before. So we assume that there is that landscape sensitivity relates to transient responses and or high uplift rates as indicators for landscape sensitivity to extreme events. So and that basically relies on the chi analysis of river profiles and the metric MCHI that I just shortly introduced. Okay, now let's take a look at the results. Now, first of all, let's see how good a simply PGA-based predictor is. So just based on peak ground acceleration. Now, first of all, well, when we look at landslide density, then if we have peak ground acceleration as our only predictor variable, then we see, well, yeah, there is some positive relationship, but there's also a lot of scatter. What we see is that what is generally known is that, well, for peak ground accelerations of less than 0.1 g, there's no landsliding response. What about looking at our damage records from hydropower projects? Well, we can see that increasing peak ground accelerations basically led to more severe damages. So for none and low, we basically have these hydropower projects in regions with low peak ground accelerations, whereas the other ones are moderate and severe in those with high PGA. But still, we have a lot of uncertainty as indicated by these little triangles that indicate the confidence bounds around these medians that are shown here as those red lines. Okay, so we can see there is generally a increase in both landsliding as well as hydropower project damage with increasing PGA, but that relation is not a very stable nor a very well confounded one. Okay, so now we look at the combined effect of peak ground acceleration and MCHI, so our river steepness index. First of all, what we see here is on the x-axis, peak ground acceleration, again going from 0 to 0.8, and our MCHI value. And what is shown here as colors is the landslide density. So we see in general that in regions with low MCHI values and low peak ground acceleration, well, we generally observe only few landslides, whereas this landslide density increases as soon as we increase peak ground acceleration and river steepness. So what about damages to hydropower? What we use here is the so-called multinomial logistic regression. So those lines that you see here, these are no regression lines. These are lines of separability, so indicating a probability of 0.5 that if we are beyond that line, we would expect severe damages for that line here, and below we would expect moderate, low, or null damages. And the same goes true for that one here, that if we go beyond that line, we would expect moderate damages, and if we go in that direction, then we would expect low or none. Okay. In general, what we see here by this multinomial logistic regression is that there is well, that first of all, PGA, peak ground acceleration, and MCHI both have an influence, but the separability of the classes doesn't work quite out nicely. So the confidence bounds around these lines basically overlap, and well, that doesn't work so well. So what we did in the next step is that we reclassified our damages into, on the one hand, none or low damages, and on the other hand, moderate or severe damages. Okay, so we only have two classes, none and low, and on the other hand, moderate and severe. Well, and then we analyze this using what is called a Bayesian logistic regression, showing here again these no or low damage, and on the other hand, moderate and severe damages. And well, the most probable line of separation is this red line here, and the grayish colors that you see in the background indicate the uncertainties about this line. And we see, well, it can vary in all sorts of directions. But what is obvious when we look at the posterior probabilities of the parameters of this logistic regression is that both peak ground acceleration as well as MCHI have a credible influence on whether no or low damage occurs or moderate and severe damage. So what can we learn from that? Well, I think that accounting for geomorphological extreme events is important and reveals limits to hydropower expansion. Now, what I've shown is that we have a nice model that we could actually use to predict damages in the wake of future earthquakes. And well, we can apply that model in, let's say, in other regions as well. And what I do here is, well, let's just apply it to the entire Himalayan arc. I'm totally aware that we have very diverse geology, diverse land use patterns whatsoever that are all able to influence how landscapes respond to earthquakes and so forth. But for the sake of this demonstration, I just would like to show a couple of results that means like applying our model to the entire Himalayan arc. Now, what we first use is, well, we need peak ground acceleration data. And what we used here is the peak ground acceleration data used by GSHAP, so the Global Seismic Hazard Assessment Program, which is a probabilistic seismic hazard assessment. And Well, what we see here are several regions that are expected to have really high values of peak ground acceleration within a probability of 10% within 50 years. Okay, so that's some data that we can directly feed into our model. Second, well, MCHI. Now that's just a topographic variable that we can derive from digital elevation models. And here I derived it from the SRTM, so shuttle radar topography mission data, 90 meters resolution all over the entire Himalayan arc. Although that is available in for that entire extent. Now, and well, combining these two data in our model then basically shows the picture that is shown here in panel C. Now that shows the severity of damage, or the probability of severe damage in response to ground shaking in these particular landscapes. And what we can see is that the model highlights, well, particularly, I mean, would have not expected it, the main physiogeographic transition, and those regions, on the other hand, that have pronounced seismic activity. So in particular, the north or Karakoram part, and down here in the Assam region, for example. So where we expect high seismic hazard anyway. But even those areas that don't have these high probabilities of a seismic risk, they are actually shown to generate earth, or might be locations where any earthquake, even of low magnitude, could have devastating effects on hydropower projects. So in general, we see that there are high probabilities of moderate to severe damages during future earthquakes for about 25% of existing, currently constructed and planned hydropower projects. So that's based on a compilation of 270 hydropower projects along the entire Himalayan arc, and for 10% of the Himalayan drainage network in general. But that Himalayan drainage network also includes all the areas that are up on the Tibetan plateau. Okay, is that a good model? Well, I don't know. It's a bit oversimplified because we just have two parameters: PGA, peak ground acceleration, and river steepness. And well, deriving these two parameters, well, at least one of them is actually quite problematic. PGA is just based on a few accelerometers and some modeling work. And of course, we know that landscape sensitivity is not entirely represented by MCHI, but also affected by geochemical properties, lithology, regolith cover, past glaciations, and so forth. However, I think that a more elaborate model that takes into account all these factors will be difficult to reconcile with the scarcity of data that we have at the moment. Well, what we know from from the Wenchuan earthquake, for example, is that landscape recovery usually takes some while, and that more damage could happen in response even after or years after the earthquake. So what we show here is just what happened during the earthquake, not precisely what's happening after that. Still, I would claim that our model, the simple it is quite helpful in characterizing the regional suitability of hydropower expansion. Still, of course, I emphasize that such a regional study cannot replace any detailed on-site investigations. However, that it can be used to assess risk of tapping the remaining hydropower potential. Okay, and with that as some key points that I said at the beginning, I want to leave you. So again, Himalayan hydropower is on a steep rise with severe impacts on the environment. I've shown that recent hydropower damages highlight the vulnerability of Himalayan hydropower. And well, that terrain analysis is actually a nice tool and provides also the measures to characterize sensitive landscapes and to predict damages. And well, that these tools can actually use to reveal potential limits, but perhaps also potential sites for hydropower expansion. Okay, thank you very much for your attention.
Thank you, Wolfgang, for your fantastic talk. So can you just close your slide?
Yes.
Yeah, it was wonderful with lots of examples and models, techniques to understand these hydropowers in the Himalayas. So I request our participants both in Facebook and Zoom, please keep posting your questions if you have anything to ask or discussion or something like that. But in the meantime, I will start some of my observation, because you as being a geomorphologist and modeler, there are lots of things in the Himalayas where these seismotectonics, or what we call the tectonic geomorphology, always playing the important role for changing this, what you rightly mentioned about the nick point. And then sometimes the nick point changes over time. And these nick points are mostly affected by the bed load generation in the mountains. So that's why it is quite difficult to measure how much sediment that sediment can be generated in the mountains. For example, you have rightly mentioned after the Wenchuan earthquake, but if you see the Chichi earthquake in Taiwan, it took nearly 5 years for the mountains settle, and it's still in the Himalayas, we don't know. So in these scenarios, how can we give some information to the hydropower developers as a geomorphologist or geologist in the Himalayas? What's your observation on this?
Yeah, thanks. That's a very good question. So as I said, what MCHI basically provides is just a topographic metric that hints at some of the more dynamic parts of the landscape that occur, and some of the responses to earthquakes are definitely more complex. As you said, the Chichi earthquake, but also the Wenchuan earthquake generated a sediment response that lasted for years, and that would have been problematic if probably there were. I'm not so aware about it, but any hydropower project would have had problems with that. I mean, the increased sediment load is problematic. So what my recommendation as a geomorphologist would be, is first of all, look at long-term data and consult geomorphologists to look at the sites and assess them properly. Also, perhaps, that's easily said, but stay away from the physiogeographic transition, which is basically an area which is highly dynamic in terms of both rivers and hill slopes. And there are safer regions further downstream that will also have probably a more balanced, a more not so peaky sediment behavior as this region.
Yeah, thanks, Wolfgang. Maybe I'll come back to you again because this is very important topic for us to understand. I'll take another question, one question from Bimal Singh in Zoom chat box. So he's asking, does your model help us to pinpoint the exact region along the river that will suffer high, moderate, or low damage that will make it very useful? Because the regional data shows entire Himalaya is a moderate and high damage area, which is probably known, but only qualitatively. What's your observation on that?
Exactly. So what I've shown in terms of images for the modeling results, this is an aggregation of the results. Okay, so it just as pixels, because showing rivers at the spatial scale over the entire Himalayan range is usually not so super useful. But in the end, our model, of course, applies to the single river reach. Let's say so what I haven't mentioned is that there is some smoothing is required, because river profiles measured with the SRTM do have some scatter in them, quite a lot of sometimes. So that smoothing is required, and that smoothing basically limits a little bit, let's say, the way we can pinpoint exactly those sites of high damage probability. Still, the smoothing is, let's say, over 2 to 5 kilometers, and I think that's the range at which we can basically make those predictions, being or still relying on just the few data that we have. We all have to keep that in mind, that it's a model that is based on just a few observations and only one major earthquake that occurred in the region.
Yeah, that's a good explanation. So we have one question in Facebook and one question in Zoom, more or less in one direction. So in Facebook, Mandira Shrestha Madam asking, what would the damage to hydropower differ according to type of hydropower, run-of river versus storage type? And same question, not same, but in exactly same line, Rana Singh is writing, what about the scale of project to be considered as recommendation, also type of hydropower recommend in the Himalayan context? Okay.
Those are very good questions. I mean, I simply brushed over the diversity of hydropower projects that exist. And you all know there are large-scale hydropower projects which either come as, let's say, dam and reservoir projects, and on the other hand, and that's something that we have more common in Nepal also, are run-of-the-river schemes. So in my analysis, I didn't make any distinction between both, and even the damages are, well, they pertain to both. I cannot, let's say, find out what exactly or which ones of both were hit harder. And so in terms of run-of-the-river projects, what we observed is, however, that a lot of the infrastructure at the powerhouse was often, like the penstock and so forth, were often damaged, and that there were some effects to the dams themselves. That, of course, also affects the reservoir and dam projects. On the other hand, well, the other one is about the scale of hydropower projects. Well, there are big ones, and there are also rather small ones, which are often community-based. Well, what we included is only those projects that have more of 1 megawatt capacity. So it's generally quite large compared to those that, let's say, are run by on a small scale. And I can't say much about those. The thing is, of course, that these can probably be rebuilt faster, better, and more directly. Which ones of those are now better in terms of sustainability, I can't say, at least not from the study that I've done so far.
Okay, thanks, Wolfgang. One question for GeoHub, Nepal. This kind of discussion, will the high resolution digital elevation model, for example, 1 meter resolution, will be helpful to point a localized area, or you can identify on a larger scale analysis on 30 meter or 90 meter SRTM images? What's your observation?
That's an excellent question. Now, well, we would all probably be forward to having 1 meter DEM for Nepal. I would love to have it. The question is whether it's useful. Yeah, I think partly yes, in particular for characterizing those areas surrounding hydropower projects directly. For larger scale studies, to my experience, such high resolution data even more creates problems rather than solves it, because there's a lot of variability within that data, and we often need to downscale it anyways to make it to be able to really work with it. So I think for for local studies, super helpful, much better for characterizing slopes and the stability than the low resolution data. For more regional studies, I think it won't make such a big difference.
Okay, thanks. So there is another question from Bimal Singh again. So he's writing, in addition to energy solution, dams are now also seen as a solution for minimizing flood hazard in the Himalayas, not only by the government, but also by the public. Therefore, now we see even more demands for big dams or high dam. Under such circumstances, how do you think as a scientist, we can address these issues, making policymakers aware? Can we have models that can help policymakers understand why high dams in the Himalayas is not or is a good idea?
Hi, Vimal. Thanks for the good question again. I know Vimal, so it's great to see him here. So the again, it's a good question. First of all, I mean, we know from the 2013 floods that those big reservoirs were actually not helping much in diminishing the flood, or we're actually not able to flood or control the flood itself. Rather, they amplified it in many ways. Okay, so some companies, I think, took the chance to see the flood wave coming and thought, well, that's a good idea to get rid of all our sediments that have been in the river and even added to the flood wave downstream then, and made things even worse. So what is needed if there is an further expansion or further development of these large-scale projects is that we have that administration and administrative control on how these hydropower projects are actually run. To this end, I mean, I think what I mentioned also at the beginning, there are these other risks associated with big hydropower projects, and often they don't turn out to be environmentally friendly at all. So that is something that should be communicated to decision makers in early stages.
Thanks, Wolfgang. I would like to request our participant to post your questions within 10 minutes if you have, and then we'll stop taking question. So one question from Santaman Reiser. I think, Wolfgang, you have addressed it, but maybe you can elaborate a little bit. Are there any relations between peak ground acceleration and landscape activities in relation to the hydropower damage?
Well, what we saw is that peak ground acceleration has an influence on hydropower damage. We can see that where there is, you know, if we are in a flat landscape, then we can actually see that higher peak ground acceleration leads to more damage, but that kind of damage is different. It's either settlement of the alluvial sediments on which dams were built. We see cracks within the dams themselves. But of course, we hardly see any of the geomorphological processes that that also impact, and that I think I have shown that have the major or one of the main impacts on hydropower projects.
Okay, thanks. From Birendra Sapkota asking, he's writing great presentation. Thank you for your insights. What additional parameters do you suggest for a more reliable model that you have presented your presentation, Wolfgang, please?
Yeah. Thanks. Great question. So I think what I have missed so far is, well, bedrock erodibility, or let's say bedrock stability, which differs widely if you do a transect from or through the Himalayan arc. So from those, let's say, metasediments to more the high-grade metamorphic rock, there's definitely an influence on how stable these hill slopes are. So that is something that I would like to include in the future. Sometimes it's a bit difficult to really sort out the differences because MChi basically is also high, where we have have the transition, the physiographic transition, which is also a lithological transition. So what we had so far, well, that's just a basic set of parameters that led to some nice results. Further refinement basically has stronger demands on the data itself. So we need basically more data, for more input data to have more complex models done.
Yes, along with this line, there's another question from Nilesh K. Jaiswara. Can we use MKI value to predict landslide prone zones? If yes, then at what scale and accuracy?
Yeah, I think we can do that. So you see that what I have done is that I restricted my analysis to the rivers themselves. And in fact, what I can show is that, well, where MKI is high, you usually have high hill slopes also. So in fact, MKI can be used to basically also make some statements about the adjacent hill slopes. And if this is possible, then it could also be possible to use it as a predictor for, let's say, landslide activity.
Okay. So now I will come back to you. My question again for a second time. The model that what you have presented there, and based on your experiences in the Himalayas, that because you have traveled, different part of Himalaya, Nepal, and India, and there is a clear in some rivers where we have already planned the hydropower. There are clear transition between bedrock and colluvial deposit within the river system. And then when the Asian monsoon coupling with this, seismically tectonic mountain zone, then we always, in the Himalayas, if you see the record, we always face the unexpected, debris flow or sediment generation. And then, we do consider this kind of activities while designing the hydropower for 100 years or some more, but still we, as being a scientist, we couldn't show our policymakers that these are the things that we can actually model from these terrain analysis or whatever you have presented. So can we show the very good model, especially focus on mountain chain in the Himalayas, to show the policymaker or the investors, for example, World Bank, Asian Development Bank, or other bank, to invest more hydropower in the Himalayan region?
As I said, it's the geomorphology. And I think we as geomorphologists or as geologists, so I mean, with a view on Earth surface processes, should have a saying or should be heard when it's about hydropower project planning. So I went through numerous hydropower, let's say, feasibility reports, assessment reports, and so forth. And to my understanding, the Earth surface process part was always a bit neglected. So there was seismic assessment, yes. There was a hydrological assessment, but there was hardly anything about sediment transport, about how much sediment basically comes down these rivers. And we can basically, we have ideas about that by either long-term data, let's say 10 beryllium-based denudation rate data, up to more recent measurements of, like the stuff that you have been doing, based on seismic or environmental seismology. So we have the means, and we have the techniques, and we have the manpower. Basically, we should be better heard, and I mean, that's two things. Well, we need to be public. We need to bring these things to the public attention. And on the other hand, well, time to take part in these discussions and environmental assessment somehow.
Yeah, you're right. It's a long way to go and discussion. So I think I will take one last question for you from Shravan Kumar Kotluti. So he's asking, what is the role of lithotectonic contact on landslides? Does it change the bedrock irradiability? Can you trace lithotectonic contact with KSN or MKI?
Yeah, hi Zavan. I didn't, as I said, I didn't look at lithological data, and even though I think it should be required in the future and for detailed assessment anyways. But of course, if you have changes in bedrock erodibility, that will have effect on, let's say, landslide zones. Often these are located on shear zones between either weak and more harder rock. And can we trace these lithotectonic contacts? Yes, of course. That's what KSN and actually MKI is the same as KSN, so we don't need to confuse that. Those are the standard techniques to actually look at these lithological differences. But sometimes it's still difficult. You know, KSN is a function of many things. It can be a transient signal that we observe. It can be change in uplift rates. It can be a change in bedrock erodibility. It could also be glacial overprinting. So it's sometimes difficult to basically draw that information automatically. It needs a good geological and geomorphological experience too.
Yes. Thanks, Wolfgang. I think I will stop here taking question. And it's a wonderful discussion, and you have presented very, very well, which is the important topic for the Himalayan context, where most of the hydropowers are planned and are being planned already financed. Some of are already financed, and lots of international banks are interested to invest money over there. So this talk might be very, very helpful for them and for us, researchers, geomorphologists, geologists, planners, hydropower engineers, and others. And thanks our participant for lively and important and pertinent questions that we have enjoyed thoroughly. So do you want to say anything, Wolfgang, before I hand over to Suraj?
Yeah, I'd like to thank you also, you and the many participants that were interested in my talk, and thanks again to you for inviting me. It was a great pleasure to give this talk. And it was a great discussion also.
Pleasure of mine also, Wolfgang, because we are working for a long and we'll work together, and it's a long way to go. So Suraj, over to you.
Thank you so much, Dr. Basanta, for the excellent moderation, as always. And yes, we'd like to thank Dr. Wolfgang Schwanghart from the University of Potsdam, Institute of Earth and Environmental Science, Germany, for the wonderful review on the hydropower in the Himalayas, a risky endeavor. It was really interesting to see the dynamics involved during the preparation of a simulation model, and how can the terrain analysis be used to characterize and characterize the sensitive landscape and predict the damages. So the case studies on the number of existing hazards and vulnerabilities in the hydropower also signify the importance of risk assessment that is very much essential for the sustainable approach. We really enjoyed the session, and the Q&A session was also really interesting with a number of quality questions. We tried our best to address all of the questions from our Facebook page live streaming and also from our Zoom chat box. In case you have any further queries, please feel free to mail us at info@inhrr.org. I would also like to convey my big thanks to all of our organizing team, speaker, session moderator, and our distinguished guests and participants for participating in this session. The session was really technical and was also really informative for all of us. We'll be sharing the recorded session on our YouTube channel, and the links will be forwarded to the registered email. Meanwhile, I would also like to share one more information regarding our upcoming webinar, so which is scheduled on the October 4, and it will be regarding, let me share my screen. Okay, so the webinar, the topic is sediment dynamics and the connectivity drive the river hazards in the Kosi Basin in the central Himalayas, which will be given by Dr. Rajiv Sinha, who is professor at Department of Earth Science, Indian Institute of Technology, Kanpur, India. So we'd also like to request our participants to please fill up the feedback survey form. Our participant can also suggest us regarding the future webinar topics, and we'll try to address them. So yes, we'd also like to mention that instead of Himalayan risk reduction, we'll be more than happy to collaborate and organize this kind of relevant webinar in the days to come. So with this, I would like to sign up from our session for today. So thank you once again. Thank you, everyone. Stay safe. Namaste. Thank you so much.
Namaste. Bye-bye. Namaste.